Hello class, Mr. Chandler here to go over the last quiz with you, graphing quiz number 2, so let's get right to it. The first problem was a graph linearization problem. We have an astronaut on a alien planet, and he or she is tasked with the problem of finding out what the acceleration due to gravity is. So they drop some rocks from varying heights, and most of you figured out this was a quadratic. Once you plotted these points and you found it was a quadratic relationship with the between time and height. That means that the height is proportional to the time squared. So then you had to go in and say, okay, I want to take these time values, and in my third column, I'm going to take not going to graph time. I'm going to graph time squared. So you squared all these numbers. You square 0.81 and square that number and put it in here, and square 1.17 and put it in. I don't remember what exactly they were. I did it earlier, but you fill in your column there. And then on part C, you're going to graph the linear graph that from your new data, right? So you're going to have height, or height on the y-axis here. We can call that delta x if you want. Displacement in the vertical direction. And we're going to have time squared down here on the x-axis. And we use these values here for our y coordinates, and these values here for your x coordinates, and you plotted a line. And it should look something like that, I think. And you found the slope of that line by using the positions on the trend line that you drew. And you should have got something hopefully about around 1.5, 1.5. And since the slope of the line is rise divided by the run, and our rise was delta x, that was on the y-axis, with delta x divided by the run, which is t squared, then we can say that delta x over t squared equals 1.5 because that's what the slope is. The slope is the rise over the run. It's a constant slope, it's not changing. So delta x over t squared is 1.5. We're going to use that information if we think about the equation delta x equals v naught t plus 1/2 at squared. The astronaut dropping the rocks is, well, he or she is dropping them, so that means that the v naught goes away. Because the initial velocity is 0. 0 times t is 0, so this is kind of bye-bye. We're left with this expression here. I'm gonna solve for a, because that's what I'm looking for. Remember g, or acceleration of the planet. We call acceleration on planets g because it's the cause of the acceleration is gravity, but every planet has their own g, right? So g on Earth is 10 or 9.8, but this planet, we don't know what it is. We're trying to find it. So we're gonna solve for a because that's the acceleration. I'm going to times 2 both sides of the expression here to cancel out the 2.5 there. Then I'm going to divide by t squared. And I'm going to get the expression 2 delta x over t squared equals a, or the acceleration due to gravity on this foreign planet. Earlier we said that delta x over t squared is equal to 1.5. So there again we see delta x over t squared. So I'm going to replace this term, delta x over t squared, with 1.5 because that's what it equals, right? It's the same thing. When I do that, I get 2 times 1.5 equals a, and then we solve for that, and we get a equals 3. So it turns out that g on this planet, or the acceleration due to gravity on this planet, is 3 meters per second squared. That is our g value. So, about a third as much as Earth, so much less gravity, can jump really high on that planet. Okay, moving on to the next section. Part 2 of the word problems. So Rolando is cruising along on his bike when he comes to a ditch. He slams on the brakes and comes to a rest before going over the edge. If he slams on the brakes and comes to a rest, that means that our final velocity is 0 because I slowed down and stopped, right? He estimates he covered about 70 meters while he was braking. Meters, that's displacement, so my delta x is going to be 70 meters. While braking at 3 meters per second squared. Meters per second squared is acceleration, so my a is going to be -3. It's negative because I am slowing down. So my initial velocity is positive. I'm slowing down, so I have to have an opposite direction for my acceleration. So I got to put a negative sign in there. Hopefully you didn't forget the negative sign. And the question asking us, how fast was Rolando going before he hit the brakes? So I'm looking for v naught. That's what I'm going to try and find. So I'm going to pick the expression. We're missing time, so I'm going to use the third expression, v squared equals v naught squared plus 2a delta x. I'm going to subtract delta ax. I'm going to subtract 2a delta x from both sides of my expression. Okay, I'm going to get v naught by itself, and that's the goal. Those cancel out, so we're left with v squared minus 2a delta x equals v naught squared. Remember, v was 0, right? There wasn't any final velocity. This whole term, 0 squared is still 0, so it's going to go away. So we're left with negative 2a delta x equals v naught squared. And now I can plug in my number. So negative 2 times a was negative 3 times 70 equals v naught squared. I multiply this together, and I'm going to get 420 positive, because the two negatives make a positive. V naught squared. Wait, I don't want to find v naught squared. I want to find just v naught. So I got to cancel that squared sign. I want to square root both sides of my expression. The square sign and square root will, the radical and the square sign will cancel on that side, and I'm left with v naught equals about 20.5 meters per second. So that's the answer for part A. Part B, Yesenia is going skydiving. She falls out of an airplane that is 4,000 meters up in the air. Unfortunately for Yesenia, her parachute does not open, and she continues to accelerate the entire time down and smacks into the ground. Ouch. How long did it take Yesenia to hit the ground? Looking for time here. All right, our initial velocity is 0 because she just falls out of the plane. She's not launched or propelled in any way. She just, just dropped. Our delta x is negative 4,000. Our change in position, right? In this case, it's a vertical change in position. She's way up in the air, 4,000 meters to start with initially. She lands, her final position is 0, the ground. So we subtract 0 minus 4,000 because she's going down to get our change in position or displacement. Wait, she's on Earth, so we know that acceleration is also negative 10 because we're on Earth, and that's the acceleration due to gravity. And we're going to find time. So again, we're going to use the second equation, delta x equals 1/2 at squared. I didn't bother writing the v naught t again because the v naught is 0, so it just goes away. This is the equation I'm left with. And I'm going to solve for t. I'm going to times 2 both sides to get rid of that half. Half and 2 cancel. I'm going to divide by a. Both sides. I'm left with 2 delta x over a equals t squared. I'm going to square root both sides to get rid of the squared sign over here. So we get t equals the square root of 2 delta x over a. I plug in my numbers, and I'm going to get t equals, let's see, x was negative 4,000, so I'll do it on the calculator here. All right, so square root alpha y equals, I want that fraction bar, 2 times negative 4,000, and the bottom I'm going to have negative 10. I get 28.3. So 28.3 seconds is how long Yesenia has to live. Part 2, how fast was Yesenia going upon impact with the ground? We're going to ignore all air resistance here. We don't concern ourselves with that. So we're going to assume she just keeps speeding up the entire time she's falling. So we're going to use the first equation, v equals v naught plus at. Remember, so this is saying that the final velocity v equals the initial velocity v naught plus a, the acceleration, times t time. We just solved for t, right? There's t right there. We solved for that, so now we know what it is. So our final velocity v equals 0 plus a, which is negative 10, times 28.3, and we get our final velocity equal to negative 283 meters a second. And again, negative sign because she's going down, right? Falling down, we call that negative. And there you go. All right, number 3, Marvin rolls the ball down a ramp. The ball is released from rest. Released from rest means initial velocity is 0. It's 3 meters long, so that's my displacement. Meters is distance, so I'm going to put my delta x as 3 meters. A photo gate at the bottom of the ramp measures the speed of the ball to be 4.25 meters a second. All right, so my final velocity is 4.25. That's the speed at the bottom of the ramp. What was the acceleration of the ball down the ramp? I'm trying to find acceleration. So this ball is not in free fall, right? The ball is not just falling in the air; it's rolling down a ramp. So A is not just going to be 10. So hopefully you didn't just put 10, thinking that acceleration is always 10. Acceleration is 10 down when an object is in free fall, when it's flying through the air, when the only force acting on it is gravity. This ball has more forces on it than just gravity. It's not in free fall. So we're going to calculate acceleration here. All right, so I'm going to use the expression. Again, I'm missing time, so I'm going to use v squared equals v naught squared plus 2a delta x. I'm going to solve for the a here. So I am going to subtract v naught squared from both sides. These cancel. I get v squared minus v naught squared equals 2a delta x. I'm going to divide by 2 delta x, both sides. The 2's cancel. Delta x cancels. I'm left with a equals v squared minus v naught squared over 2 delta x. Now I can plug my numbers. Let's see, v squared, the final velocity is 4.25 squared minus 0 squared is 0 divided by 2 times 3. And I'm going to get my answer to be 4.25 squared divided by 6, about 3. About 3 meters per second squared. All right. Part 3, translating graphs. So we have 2 position time graphs and then some velocity time graphs. So I asked you to just sketch the graph. Sketch means don't worry about finding the actual slope or anything. Just give me the general shape of the graph. You don't have to worry too much about being precise with your slopes and stuff. So this is a positive slope right here. This is a negative slope right here. So all we're saying is if the slope is positive, right, then the velocity is positive. So, and it's constant, right? It's not changing for this time period. It's a straight line, no curves. So constant positive velocity. So that would look like this for the first about 8 seconds. So somewhere in there. And then suddenly we have negative slope for the rest of the time. Negative slope means negative velocity. So we go, we go down here. Oh my gosh, I can't draw straight lines on this pen pad I have. Very difficult for me. And here negative, and then we draw a flat line at negative, right? So we're positive slope, positive velocity, negative slope, negative velocity. All right, the x here, this is a little trickier because it's got some curves to it, but we'll see how it goes. Here, we're pretty constant, but then we see we flatten out right here. We get flatter, and we get flat there. And then we turn around and go back the other direction. So this is showing us negative velocity because the slope is negative. It's getting flatter, and we just slow down, stop here, and then we start to get steeper in the positive direction. Now we're going up, right? So we start off negative, going down on the graph. We get flatter, flat. We turn around. Now we're positive, going up on the graph. That means we turned around, and we're getting steeper and speeding up. So it's going to look something like this. Okay, it's just showing us getting, slowing down, getting flatter in the negative direction. Negative velocities over here, getting right here at the bottom. That's when we cross the x-axis right there. Then we start to speed up in the positive direction as we get steeper. And then in here, we're going to flatten out. We get flatter, we slow down, and then at the end we're pretty much flat. That means no slope, which means no velocity. So something like that. Some general idea. It's kind of hard to tell sometimes. You're taking the quiz. Is that a straight line there or not? If you interpret it that way, that's okay too. It's hard to tell. I did these by hand, so not perfect. But if you get I'll know if you understood what you're doing. All right. Below is a velocity time graph. So we did this one in class, but I'll do it in the video too in case you want to see it again. All right. So velocity time. First thing I'm going to do is translate the graph. It says translate the graph into the position versus time graph, then answer the questions that follow. So, all right, here we have an object that is speeding up in a negative direction. The numbers getting bigger, 1, 2, 3, 4, 5, and they're all negative, so go in that direction. So we're going to curve, we're going to get steeper. Then we have a short period here where we have constant negative velocity. So that means we have a line that's straight, not curving for this time period here. Let me draw better. All right, it's all, hold on, I can do better than this. There we go. Now here we are slowing down. We're going back towards zero velocity. We're going -7, -6, -5, -4, -3, -2, -1, 0. So our numbers are getting smaller, but they're still negative. So we're going to flatten out. We're still going down on the graph, down for negative. So we're going to flatten out here. Look, let me do better than that. Something like this. And then at the end here, this is zero velocity. We're a flat line, and we're on the zero line here, right? The x-axis represents zero velocity. So we're at zero velocity here. So we should have no slope, zero slope here at the end of the graph. And that's what I tried to draw there. Okay? Okay. Describe the motion of the object based on the graph in a sentence or two. So I'll say it again. We speed up here in the negative direction for about 6 seconds, looks like. Then we have constant velocity in the negative direction for another 5 seconds. We then slow down while moving in the negative direction for about 4 seconds. We then come to a stop or come to rest. Oh, sorry, hold on. We then come to a rest at 15 seconds, and then we're at rest the rest of the time. There you go. What is the acceleration of the object from t equals 1 to t equals 6 seconds? So that's this line segment up here. We find the acceleration on these graphs on a velocity time graph. We find the acceleration by finding the slope. Find the slope, find acceleration. The slope is going from here to here. It goes about down 7. So the rise is negative 7. Divided by the run, which is over 6. So negative 7 over 6 is acceleration will be negative, let's see, 7 over 6 is 1.7. So negative 1.17. 1.17 meters second squared. And the very last question asks us, what is the displacement of the object from 0 to 20 seconds, so the whole time. So displacement we find on a velocity time graph, displacement is found by finding the area under the curve, which what we really mean by that is the area between the x-axis and the line of the graph. So here we have a triangle. We're going to find the area of that triangle. Here we got a rectangle. Find the area of that rectangle. Here we have another triangle. Find the area of that triangle and add all the areas up, right? So area of a triangle is 1/2 base times height. So 6, base of 6, height of 7, negative 7, and half of that. So that'll be 21. So negative 21 there. Right? We're going in the negative direction, so it makes sense that our displacement will be negative. Here we have a rectangle, so the area of that is base times height. So 5 base, height is a negative 7, so it's negative 35. And here we have a base of 4 and a height of negative 7, and half of that, so negative 14. We add it all up, and our displacement, delta x, is going to be negative 70 meters. Okay. All right, and that's the whole quiz. So you can replay this a million times and go over it. If you have any questions still after watching this video, please come see me. Let's talk about it together. Let's go over it. Let's practice, and get better and keep on keeping on. All right, have a great time, a great day, a great weekend, whatever it is when you're watching this. Bye-bye.